Hey everyone, and welcome. Today we are going on a journey to the absolute smallest scale you can imagine to unlock the secrets of the atom. You know, the fundamental building block of, well, everything. So let's jump right in.
Okay, let's start with a little thought experiment, one that people have been thinking about for thousands of years. Imagine you've got, say, a piece of gold. You cut it in half. Then you cut one of those halves in half again, and again, and again. So could you just keep doing that forever? Or would you eventually hit a point where you have a tiny piece of gold that you just can't cut anymore?
Way back, over 2,000 years ago, a Greek philosopher named Democritus thought he had the answer. He was convinced you'd eventually reach a final fundamental particle that was completely uncuttable. He came up with a name for it, atomos, which in Greek literally means indivisible. For him, that was it, the end of the line. A brilliant idea, for sure, but that's really all it was back then, just an idea.
So for centuries, the atom was just this cool concept, purely philosophical. To turn it into actual science, it needed proof. It needed some ground rules. Scientists first had to prove that the stuff that makes up our universe, matter, actually behaves in ways that are predictable, consistent, and measurable.
And they found those rules. First up, you have the law of conservation of mass. Pretty simple, right? It just means that if you start a chemical reaction with 100 grams of stuff, you're going to end up with 100 grams of stuff. Matter doesn't just poof out of existence. Then there's the law of definite proportions. This one proved that a specific compound, like water, is always made of the same elements in the same exact ratio. Water is always 2 parts hydrogen, 1 part oxygen. Always. These rules were a huge deal because they suggested matter wasn't some kind of infinite mush. It had to be made of distinct, reliable little units.
And this is where a guy named John Dalton comes into the picture. He was the one who brilliantly connected these new scientific laws all the way back to Democritus' ancient idea. He put it all together to create the very first comprehensive scientific theory of the atom. I mean, Dalton's theory was a total game changer. He proposed that every element is made of these unique, tiny, indestructible particles he called atoms. And he pictured them as these hard, solid little spheres, kind of like tiny billiard balls. He figured atoms of, say, gold are different from atoms of iron, and that they combine in simple whole number ratios to make everything around us. This simple model was perfect. It neatly explained both of those scientific laws we just talked about.
Now, Dalton's solid sphere model was a masterpiece for its time, but you know how science works, right? It never stops asking questions. And it wasn't long before new experiments started to show some cracks in that whole indivisible idea. It was starting to look like maybe, just maybe, there was something inside the atom.
Enter J.J. Thomson and his wild contraption, the cathode ray tube. Think of it like a really, really old-school TV. He passed an electric current through this vacuum tube and saw a glowing beam. But here's the kicker. When he brought a magnet nearby, the beam bent towards the positive end. Well, that could only mean one thing. That beam had to be made of tiny particles with a negative charge.
And just like that, Thomson had discovered the first subatomic particle, the electron. This meant the atom was definitely not an indivisible sphere. To make sense of this, Thomson came up with what we now call the plum pudding model. He imagined the atom was this big ball of positive pudding, with these little negative electrons scattered all through it, like plums. It made sense, right? A logical next step.
But how do you test a model for something you can't even see? Well, one of Thomson's own students, a guy named Ernest Rutherford, came up with an absolutely brilliant experiment. The plan was pretty straightforward. He was going to shoot these tiny, positively charged bullets, called alpha particles, at a super thin sheet of gold foil. I mean, this foil was only a few atoms thick. If the plum pudding model was right, those alpha particles should have just punched right through, maybe getting nudged a tiny bit.
The results were, well, they were completely shocking. I mean, mind-blowing. Sure, most of the particles did fly straight through, just like they expected. But some got deflected at really sharp angles. And this was the part that changed everything. A tiny, tiny fraction, about 1 in 8,000, bounced almost straight back. Rutherford later said it was as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you.
This bizarre result could only mean one thing, and it completely changed our picture of the atom. For most of the particles to get through, the atom had to be mostly empty space. But for a few to ricochet back so violently, they must have smacked into something incredibly small, incredibly dense, and positively charged. Rutherford had discovered the atomic nucleus. The plum pudding model was toast.
All right, so after all that incredible detective work, from Dalton to Thomson to Rutherford, we've finally got our main players. The fundamental pieces of the atom have been revealed. So let's take a second to formally meet the particles that make up pretty much everything. So here's the lineup. You've got the positive proton and the neutral neutron, both packed together in that tiny, dense nucleus at the center. These two account for basically all of the atom's mass. Then, flying around that nucleus in a huge cloud of mostly empty space, you have the negative electron, which is just incredibly light in comparison.
So what's each one's job? Well, the number of protons is the atom's ultimate ID card. It's non-negotiable. If you have 6 protons, you are carbon, period. The electrons, on the other hand, are the social butterflies. They're on the outside, and they're responsible for all of chemistry, how atoms bond, react, and interact with each other. And the neutrons, they're kind of like the glue. They add mass and help keep all those positive protons from flying apart in the nucleus.
Okay, so just when you think you've got it all figured out, nature throws a curveball. It turns out that not all atoms of a single element are perfectly identical. You can actually have a few variations.
Let's start with isotopes. Look here at carbon. Both of these atoms are carbon. Why? Because they both have 6 protons. That's the rule, remember? But look closer. Carbon-12 has 6 neutrons, while the famous carbon-14, used in carbon dating, has 8 neutrons. So it's the same element, just with a different number of neutrons, which means it has a different mass.
And then you've got ions. Normally, an atom is neutral. It has the same number of positive protons and negative electrons, so the charges cancel each other out. But check out what happens with this sodium atom. It starts with 11 protons and 11 electrons. If it loses one of those electrons, it still has 11 positive protons, but now it only has 10 negative electrons. That imbalance gives it an overall positive charge, and just like that, it's become a sodium ion.
All right, one last puzzle for you. We know that an atom's mass comes from its protons and neutrons, and we count those in whole numbers. So why is it that when you look at a periodic table, the atomic mass for an element is almost always some long decimal?
The secret is that it's a weighted average that takes isotopes into account. See, in the real world, any chunk of an element is actually a mixture of its different isotopes. Take silicon, for example. More than 92% of all the silicon atoms in the universe are the silicon-28 isotope. But there are also small amounts of silicon-29 and silicon-30 mixed in there too.
So, that atomic mass on the periodic table, it isn't the mass of just one single atom. It's the weighted average mass of all of silicon's isotopes based on how common each one is. And when you do that math, that's how you end up with a decimal. It's a number that perfectly reflects the natural mix of that element here on Earth.
We have come so far, from a simple idea to a solid ball to a tiny nucleus. But Rutherford's amazing model left everyone with one huge nagging question. Basic physics tells us that opposites attract, right? So why don't the negative electrons, whizzing around in all that empty space, just spiral down and crash into the positive nucleus, causing the whole atom to collapse? The fact that they don't, the fact that you and I and everything else is stable, tells us there's another, much stranger layer to this story. But that, well, that's a story for another time.